Greetings. Welcome to presentation 3.1 on wood and lumber. I'm going to discuss a couple of different topics in this first of a few lectures on wood. We're going to talk about the very unique property of wood, that being that it's a living building material, unlike all others. And what comes with that is the defects. Comes with defects. And then how we evaluate those defects and grade them, and then cutting lumber, and the very important topic of moisture content in wood. So, getting started, a little terminology. Hardwood and softwood, common way to classify woods. The names, however, could be a bit misleading, as hardwoods are not necessarily harder than all softwoods, and softwoods are not necessarily soft, so it doesn't really tell us exactly what it kind of suggests that it might be, actually. Softwoods have pine needles and are not deciduous. They keep those needles throughout the year, and hardwoods typically are deciduous, where they drop their larger, broad leaves. And it points out here that well-known balsa wood, which is a hardwood, is actually very soft, and softer than any commercial softwood. So that's what we build our architecture models with, very, very soft hardwood. So in general, what do trees do? What does the wood inside the tree actually do? So conducts water and nutrients up to the leaves and the tissue where it's needed, and it allows the tree to stand up for itself. So that's the trunk. This is the usable part for the builders, typically for us. So a little bit about tree growth. So essentially trees grow new skins, basically kind of consuming their existing skins, and so it says here it increases in diameter by the formation of a new woody layer. So that's the skin. It occurs between the existing wood and the inner bark. So here we are at the bark. Here's the inner bark right here, the yellow, and then this would be the new skin growth right there, consuming the sapwood and the heartwood inside. So sapwood, it's right here, that's next on the outside of the heartwood. So the sapwood, this is the youngest, the outermost wood. We could see it here, this light ring on the outside, and we could see it here in cross section as well. So what this does, it conducts the water from the roots up to the leaves. All wood in a tree is first formed as sapwood. So this is everything. This heartwood on the inside was originally sapwood. So the more leaves in trees, the more leaves that a tree has, the more vigorous its growth, the larger amount of sapwood is needed to move those nutrients and water up. So therefore, the conclusion is, hence trees making rapid growth in the open have thicker sapwood for the same size than trees of the same species growing in dense forests. So trees that are out in open areas that are allowed to grow more robustly than trees in forests will actually have more sapwood. So depending on where the tree is living, growing, could affect the inside properties that we are concerned with. Here, this is just a nice image that illustrates this point. So here we have an 8-year-old tree, just a little twig, and then as it's growing, it's consuming the sapwood is consuming what is the heartwood on the inside, and everything that was at one point sapwood is becoming heartwood. So there we have it at 8, 10, 12, and 22 years. So kind of consuming itself. Moving on, and then odd images, but especially this one. Secondary growth also could consume foreign objects, such as metal posts and things that are were at first at a little bit of a distance from the tree, are now being consumed as it grows. Okay, then that was the sapwood on the outside, and now the heartwood on the inside. This is the dark brown area here. Once heartwood formation is complete, the heartwood is actually dead. It is more resistant to decay than the outside sapwood layer. Its appearance in cross-section is usually a dark-colored circle here, and it follows the growth of the rings. So these are the growth rings, all of these different rings, the various rings. Heartwood may be much darker than living wood. Okay, and then this here is a cross-section through a trunk, and it shows 27 annual growth rings. So that's 27 years they count in on those rings. And it also says here that the dark radial lines are small knots, also important. We're going to talk about knots very soon. So these were branches, and now what they leave behind are knots. Here's another cross-section. There's the heartwood in the middle, surrounded by the sapwood on both sides. This has been cut the length of the tree, not in short cross-section. We're not looking at the circle, we're looking at the length of it now. And then here's the branch that has become a knot. All right, so here we see a tree growing again. Young trees are often covered with limbs almost, if not entirely, to the ground. So here we see the young tree covered in branches, top to bottom. Eventually those branches die and fall off. And then it points out here, importantly, subsequent growth of wood may completely conceal the stubs. However, the knots do remain. So no matter how smooth and clear a log is on the outside, it's more or less knotty inside. So this tree, although it has a clean appearance on the outside, there were branches originally, and so there are knots, in fact, behind what might appear to be a clear log. So consequently, the sapwood of an old tree may be more free from knots than the inner heartwood. So that just follows up on that. All right, now getting to the back to the annual growth rings, which we see so clearly here. Again, so for each year, this ring represents the growth. So where there are clear seasons, as there are here in Philadelphia, growth can occur in a discrete annual or seasonal pattern, leading to growth rings. So that's what those are. However, if there's no seasonal differences, like this image I found of a palm tree cross-section, there are no rings, in fact, because there is no change in season, so it can't be recorded in such a fashion. Here's another cross-section. This one, these are two separate ones. This one's very old, came from a roof beam, and cut by scientists approximate in about 1070 AD. And very interestingly, it says here that when scientists are looking at this, they could see that there were droughts in these years. So tracing back, they could actually count on when droughts occurred. Very interesting, I think. Okay, moving on to cutting the lumber. Now that we've examined the inside of the tree, this is very important. So depending on how we cut a piece of lumber out relative to the geometry of the trunk, it affects the properties. It affects the properties of the piece of lumber. So here at the top we have flat sawn or plain sawn lumber. So this is where the end grain is cut, or the cut is made at approximately 182 or parallel with the face. So right there. So it's the least stable cut. That's very important, that fact. So least stable, and we'll zoom in and we'll see some pictures of these. But this is the cut that would cup, would tend to cup and follow those rings. Here, well, no, so let's not look at rift sawn first. Let's look at quarter sawn. This is the most stable cut, premium lumber. So here, quarter sawn, the end grain is nearly 90% at 90% right angle to the face of it. So here is the grain running up and down, and this is the best, most stable lumber that you could achieve. Here, rift sawn, this is somewhere between the two, where the end grain is coming in between 30 and 60 degrees relative to the face of the board. And here is a combination of the two. Very common to find plain sawn lumber in the pile. So somewhere between the two. So this is flat sawn, least stable, quarter sawn, most stable, rift, and a combination of rift and plain. This is the middle ground where we'll find most of our lumber. All right. this image here in this chart, this graph here on the right, is basically telling us, or showing us how a sawmill would look at a tree, essentially determining how it could profit, what's needed per orders, and then how it will profit. So there are only so many cuts, premium cuts that could be made out of a log. So it all has to be calculated before they start cutting. And here they're showing the different saw lines coming through, squaring it up and then breaking it down. Okay, so some terminology we have to discuss now. So longitudinal, this is in the direction. So these definitions are not specific to trees. These are just more geometry, actually, but just so that when we discuss the tree trunk and how it's cut, we need the vocabulary to do so. So longitudinal, this is in the direction of the length of the primary axis. So this is our tree trunk. This is a longitudinal. This is the longitudinal direction in line with the trunk. Transverse, lying or extending across or in the cross direction. So basically we're cutting through, and we see this would be a transverse section as opposed to a longitudinal section. If we cut a blade right down the middle, we'd have a longitudinal section. Here we've cut at 90 degrees and we have a transverse section. You could also describe rooms in the same fashion. If it has a long axis, that would be a longitudinal building section cut through it, as opposed to here we're cutting through at 90 degrees, and that would be a transverse section. Here, ray, you might remember from geometry, so one of a system of straight lines emanating from a point. So here's our center point, and the rays are kind of shooting out, and they correspond to the early tree trunks, or tree branches, not the tree trunks. And then tangential. So this is touching at a single point, has to be tangent. So again, from geometry, we have a circle, and then we have a line just touching, just kind of brushing along that circle. That is a tangent cut. And we'll see some more images of that. But these are just basic definitions that we need to be familiar with. Okay, so here is a piece that has been cut. So wood is cut longitudinally in two different planes, tangent or radial. So again, longitudinally is in the direction of the trunk. So this cut was made longitudinally, and this one as well, not the cross section. So the tangent cut is made running the saw blade down, and it is coming in tangent to the circles. Or radial is coming like a radius, and it's cutting right in half. So tangential sections are made tangent to the rings. That's what we just discussed. Also, this plane is also what we call the plane sawn lumber. And what the result is here. We see the irregular wavy patterns of the rings that have been cut when we have a tangential cut. So this is the common appearance of the face of a board. Of the board being dimensional lumber, a 2x2, a 2x4, 2x6, etc. That's what we're talking about when I say a board. Okay, so now we see several boards being cut out of this trunk. So radial sections are made along the radius of the log and at right angles to the annual growth ring. So that is here. This is the quarter sawn lumber we're talking about. The radial sections produce the quarter sawn lumber right there. And we see the rings appearing at 90-degree angles to the face of the log, of the face of the board. This would be the face, and this is coming in at 90 degrees to that. So this is again the premium, most stable quarter sawn lumber. And as it points out here, rings appear like closely spaced parallel bands. That's what we see right there very clearly. And this just points out that there are only so many of these premium boards to take. Therefore, they're more expensive. And this is the plain saw lumber, not as stable. Okay, so cutting them. So boards with straight grain, these are cut again longitudinally in the direction of the trunk. So the cut along the length of the tree trunk, resulting in the greatest wood strength. So this is our lumber. This is how we cut it. However, it could also be cut kind of in cross section or perpendicular. So this is cross grain boards. This is cut across the grain, roughly perpendicular to the tree trunk. This results in the least wood strength. And these are boards are rarely used for this purpose, only decorative or for some small scale like a butcher block, as we see here. And here I just dug up a couple images quickly, looking for, again, cross-grain boards. So here, just simply decorative, kind of a backsplash. I don't find it particularly interesting myself. Here, however, they're putting it down as a floor, actually. So this, I would say, is just a bad idea. I've never actually seen it in person, and not something I would do in my house, that's for sure. These, essentially, think of these rings. Think of them as straws, essentially, moving up and down the tree, taking that water. So here is where the wood is most vulnerable and susceptible to soaking in water and damage. So I would not. I just think this is a bad idea. Flooring would really rarely ever done like that for a good reason. All right, moving on to knots, defects. All right. A knot is a particular type of imperfection in a piece of wood, and it affects the technical properties of the wood. So this is what we care about, what happens. So longitudinally sawn plank, that's what we have here. A knot appears as a rough circle right there, and the grain of the wood kind of flows around it and then kind of rejoins on the other side. So that's what we're looking at there. We're looking at also more specifically a branch that would be coming out of the trunk. This is the trunk beyond, the branch would be coming out, and it got sawn through at this point. Okay, so in grading lumber and structural timber, knots are classified according to four things: their form, so that's their three-dimensional form; their size as an object; the soundness, so how hard the knot is itself; and the firmness with which the knot is held in place. So this is what people who are grading look for. Four different ways to describe knots. The firmness is affected by the length of time for which the branch was dead while the attached stem continued to grow. So again, natural product. Knots materially affect cracking, checking, warping, ease of working or workability. That's a term we'll use quite a bit. And cleavability, cutting of the timbers. They are defects which weaken the timber and lower its value for structural purposes. So knots are not good things. And these are some defects, specific defects. So here's the board, and a bow is warped on the face of a board from end to end, so it's dipping in this direction, essentially. A cup, hollow across the face of it. So again, this is going back to that least stable plain sawn lumber. This is what it would be prone to do. It would be prone to cup in the same direction of the rings. A crook is warped along the edge line, or a crown. So this would be the crown out here. This is the edge line. This is showing how it's displaced, essentially. So when carpenters are assembling walls, they will sight down the 2x4 or the 2x6 and identify where the crook is. Most have a crook. They're going to face one way or the other, and then they will put all of the crooks face down, typically, and then they'll stand the wall up, and then all the crooks will be facing in the same direction. So that way they're not stressing the drywall that would come later. And similarly, when we look at beams, or when we build a built-up beam out of something larger, 2x8 or 2x10, 2x12, we'll also sight them and put all the crooks up as well. Okay, splits here, crack going all the way through the piece of wood, commonly starting at the ends, twisting, multiple bends, and checking, kind of looks like a crack but does not actually pass through the wood. Those are some common defects. Alright, so on to grading here. So there are two different methods for grading wood. One is visual inspection. That's what we see both of these pictures are. We see these inspectors sitting and grading the wood as it passes in front of them. The other is machine testing. So visual inspection requires a trained and certified lumber grader. That's these gentlemen again, to inspect it and assign a grade based on characteristics such as knots, wane, and slope of grain. So we discussed the knots, we discussed the slope of the grain, and the wane would be when an edge of a board is missing. I'll see if we can see a picture of one of those, but it's essentially when a corner, when it doesn't have a sharp corner and it was kind of that's missing along the edge here. The highest visual grade for framing lumber is select structural, and then in order 1, 2, and 3. So 3 is the bottom. So often you'll see notes on framing plans that will say number 2 or better, for instance. And here's machine testing. So mechanical testing uses testing equipment such as this piece and this piece behind the gentleman. They measure the actual properties like stiffness and density. So machine stress ratings, or MSR, and mechanically evaluated lumber, MEL, assign a specific grade to it. And they're much more detailed, a lot more specific about the different structural characteristics of a piece of lumber. So they're typically not used outside of truss and glulam manufacturing. So not common dimensional lumber would not be machine tested. And we'll talk more about trusses and glulams in the next lecture. Okay, so concluding, I think, on this issue is no matter which grading process is used, the lumber grade corresponds to a set of structural properties that predict how the lumber is going to behave in all of these different structural forces that they experience. So compression, tension, bending, shear, deflection. That's all the different ways that structural members get pulled and pushed and bent. All the different structural experiences that a member would go through. So the lumber grade tells the engineer how it's going to behave, and the engineer will assign a grade based on what it has to accomplish structurally. Okay, moving on, I think, to the final topic is that of moisture content. Very important topic, again, for a living material. So here we have a moisture meter that is being inserted into a piece of wood, and this is what we see on the screen. So MC is moisture content, and this would have read at 6.2%, and we'll talk about those numbers. Okay, so looking inside of a tree, we have a lot of moisture. Moisture exists either as bound water, which is held inside of the cell, or free water, which is stored in the cell cavities. Two different types of water. As freshly cut or green wood dries, so we just cut down the tree, the free water is going to evaporate first. Here's a very important point, the fiber saturation point. That is reached when all of that water is gone, leaving only the bound water in the cell. So here's the bound water, the green that remains. The free water is the first that dissipates. When all that's gone, it's reached its fiber saturation point. All right, the fiber saturation point averages about 28